you look at the syllabus, and I know you'll notice that I've built in a fair amount of open space. So for example, we have the exam 1, and then within that space, though, we'll have some time to review. I always make time for review. And so then we have here, I've written a review, academic holiday review, and then the last week review. So I don't want to just hammer you guys right up until the exam. I want to give you a little chance to breathe and ask questions. So I think the material so far has been reasonably straightforward. And but again, if you have questions, come see me in the office. All right, so I'm going to, let's start with the slides. A couple of things I want to go over. So today we're going to continue our equations from 11.1 to 11.4, specifically with projectile motion. We're talking about rectangular coordinates in 3D. And I want to note, though, if you are reading the book, it can 11.4b is a little bit of gibberish when you read it. And all it's really saying is that you take the derivative of vector quantity, it's equal to the derivative of its components. And I think it could have been said a little simpler, but that's it. There's nothing earth-shattering in that. I know some in the past have criticized me for being too light on the theory behind the class. A lot of the stuff we're talking about right now, though, is still physics review. And so we're just going to accept the equations that we started with for linear motion and projectile motion as given. So I'm not going to go back and derive those from physics. So, but as we go forward, I will try to integrate more, no pun intended, more background, and so that you guys don't know, have an idea of where this came from. So thank you. I think everyone's muted now. Good. Okay. All right. So two-dimensional motion. And so no different than what we've been doing, motion that can be defined by initial velocity and gravity. And so we have in the examples we're going to do today, we're going to have constant acceleration, or it's going to be a function of time, the acceleration. And as I said, is the 2D usually involves projectile motion. And so if we think about that, if we write it out, what we're really saying is that if you have, for example, before we started off with a line and we just talked about motion down and up the line, but here if we take a curve like this, and let's say we have a distance r to this point, then we know that at this point P, and then we say we move, this point P moves to this point up here, which we'll call P prime, then we have then R prime. And so we can define this move from P to P prime as the change in S, the change in position. And so really what we're doing then is if we have the change in position, we know that our velocity then is just the dr dt. And then the acceleration then is dv dt. So it's really no different than when we talked about dx tt and dv dt, just going around on a circle. And so the difference really in curvilinear is that we're going to treat the x and the y directions independently. And so if you have, for example, a particle in space, and so here's your axis, and you have some random particle in space, and it's moving along some curve, then we can draw a vector to that particle. Sorry, it's not the best drawing. Let's draw it up to here. We can draw a vector to that particle, and we can define its location as xi plus yj plus zk. And there, what we've done is we've defined it as where it's at. And then if we have, say, a second particle, say it moves up to here, another r prime, then this is going to be x prime I plus y prime j plus z prime k. But again, the motion along that line is then again just given by v equals dr dt. And so what we end up with is our velocity in the x, I, plus velocity in the y, j, plus velocity in the k. I'm sorry, velocity in the z, k. And same with acceleration, a equals dv dt. In that case, we have axi plus ayj plus a zk. So the point of showing you this is just saying that whether it's moving in 1 or 2 or 3 dimensions, you don't really care because you can treat each one individually. And so that's what we're going to do when we solve these projectile motion problems. And you probably remember from physics that if I launch a projectile, you know, just on a nice simple one where it's just a flat surface, you have an initial angle here, and then you have your final here, that you have your y equation, y naught plus v naught in the yt minus 1/2 gt squared, right? And that would give you the time, that would tell you how long it took to go up and down. And so if you know then, for example, what the initial velocity in the y, which in this case is just going to be v y naught times the sine of phi, then you can then solve for time, assuming you know this distance. And if you know the time, then you can then relate that back to the x, the same equation in the x. So x is going to equal x naught plus x naught, I'm sorry, x naught plus v naught in the x times t plus, and then usually there's nothing here because in projectile motion, we don't have an acceleration in the x. So we just limit it to this equation. All right. So question? Okay. So this should be, I mean, this stuff here is like physics 144. It's not anything that you haven't seen before. But nonetheless, I want to review a couple of problems, and so that we can go through and you guys will have mastered that before we move on. All right, so here in this example, we have a slow pitch softball, underhand pitch, and we're told that it has to reach a maximum height that's between 1.8 and 3.7 above the ground. I don't know where that came from or not. I'm not a slow pitch softball player, so, but so we're going to try to figure out is, given the criteria of having to be between 1.8 and 3.7, does it do that given the initial velocity of 13 meters per second at an angle of 33 degrees? And then we want to, so we're going to basically find the height, and then we're going to find the height of which it lands. Okay. So if we look at our, and that's why I gave you, hopefully everyone downloaded the sheet so they have this in front of you, or you can have it on their screen, but I'm going to stop sharing now and I'm going to go back to my, my screen. There we go. And so we start off, we have 0.6 and we have our initial velocity and we have our angle. Let's call it theta. So we know that V naught equals 13 meters per second. And our initial Y distance is 0.6 meters. Okay. And
Professor?
Yes.
Someone's in the waiting room waiting to get in.
Oh, are they? I'm sorry. I usually see that. Let me see. Ah, there they are. Thank you. Got to show up on time. No slackers. But thanks for pointing that out for me. Okay, so getting back to this, we have this distance, and now we're going to want to find, we know it's going to fly through the air and it's going to land somewhere over here, and we want to know what is this final height, where's it going to hit. All right, So that's our what we're finding. Now, you'll notice that in all the problems I've done so far, I haven't done any free body diagrams really. And there's a reason for that, is that we're not really at that point yet. And so when we get into chapter 12, we will be doing lots of free body diagrams. So rest assured. All right, so we know when we're doing in the homework, you do have a projectile motion. So we know that the equations that we want to usually use are for motion in y direction. That's going to be Vy equals Vy naught sine theta minus gt. Okay, so that's our velocity. And then we also have our equation y equals y naught plus v naught in the y sine theta times t minus 1/2 gt squared. Okay, so we know that when we reach y max, the maximum height, that means that the velocity in the y is equal to 0. So if we go ahead and solve for t, then in this first equation, we call that equation 1 and equation 2. Then if we solve for this to be 0, then we know that t is going to equal 13 sine 33 over 9.8. Okay, so our t then is equal to 0.7222 seconds. And so this is the time to reach max height. Okay, so far so good. So now from that, now that we know the time to reach max height, then we can go back to our y equation and we can figure out where it will be at max height. So now we come in and we write out our y max equation. So y max is going to be equal to initial height, which was 0.6, because that's where it started, and then plus the speed, 13 sine 33 degrees, times the time, 722 seconds, and then minus 1/2 9.8 meters per second squared, and then times 0.722 seconds, and that's squared. Okay, so we solve that, we get y max is equal to 3.16 meters. Okay, so our original problem told us that it had to be 1.8 less than or equal to, with a maximum of 3.7. And so looks like we're right in that range, 3.16. All right. So again, so far we haven't done anything tricky. This is stuff you could have done not even having taken the class, but this will lead us into the next more complicated problem we're going to do. And on Monday we're going to do a projectile motion in the air, but we're going to combine it with relative velocity. And so by the better you understand this at its basis, then the easier it'll be when we start adding stuff that's a little bit beyond what you saw in physics. All right, so the second part of this B is to find the horizontal motion. All right, and the reason we want the horizontal motion is we want to know is how far does it go in, what is the time that it takes to go this distance over here, which I don't believe we know. Oh no, we do. I'm sorry. This is 15.2. That's right, 15.2 meters. So the reason we want to find out that time is because if we know the time it takes there, then we can plug that back into our y equation, and we can figure out what height it is when it's at that time. So the time it takes to go from here to here is the same time it's going to go up to its apogee and then back down. And then we can determine how high it is at that time that it took to go this distance. Okay. So horizontal motion is just x naught equals, I'm sorry, x equals x naught plus v naught cosine theta times t. And so in this case, we have 15.2 meters equals 0 plus 13 cosine 33 degrees times t. And so we solve and we get a t equal to 1.394 seconds. So we know that that's the time it takes for it to get to travel in the x distance of 15.2 meters. So now what we want to know is if it goes up and down, and when it's flying in the air for 1.394 seconds, where does it land? So what is that height? Okay. And so what we're going to do is we're going to say y equals y naught plus vyt minus 1/2 gt squared. Again, I listed the equation. And so what do we have? We have its initial height is 0.6, and then plus 13 sine 33 times 1.394 minus 1/2 9.8 meters per second squared, and then times the time again, 1.394 seconds squared. There we go. Sorry, my chicken scratches. And so we get a y value equal to 0.937 meters. And that's reasonable. That's about a little under 3 feet or around 3 feet. And so that's a reasonable place for the ball to land. And so another thing to always consider when you're looking at your answers is, do they make practical sense? Because just like in statics, I'm not going to give you a problem that's ridiculous. So if the ball landed 15 meters above the person's head, then obviously there's a mistake somewhere. One other thing too is on the homework, I did repost it with all the answers. And on number 2, the distance was 300 feet for the car. And then for some reason, when I wrote it out, I wrote 100. So I apologize for that, but it's 300 as it is in the picture. And I put a note on that when I sent that out to you guys yesterday. So just a reminder. Okay, so any questions on this one? Pretty straightforward. Good. All right. So let's look at the next one. And again, increasing complexity. So in this one, we have a worker and they're trying to shoot water up into to clean out a tube. And so the idea is how high, for one, is what does the angle need to be in order to reach the top, and how far can they shoot the water? And so we're given initial velocity 11.5 meters per second. And so what we really want to know is what is the angle that that individual is using and how far does that water go? All right. And we know the top of the pipe's 1.1 meters. All right. So if we go back to this, here's our drawing. So we have 11.5 meters per second V naught. We have alpha. There's our D. That's what we're trying to find. 1.1 meter height. So we want to find this and this. Okay. So again, we're going to use our basic equations. So go ahead and just write it on here easier. So we're going to have Vy equals Vy naught minus GT. Okay, so for velocity there. And then of course we have y equals 0 plus V naught t minus 1/2 gt squared. Okay, so we can we know that the velocity initial in the y is going to be equal to 11.5 sine of alpha, and we know the velocity in initial in the x is going to be 11.5 cosine alpha. All right, so if we rewrite our Vy equation, we get Vy equals 11.5 sine alpha minus GT. Okay, and then we can also rewrite our Y equation as Y equals 11.5 sine alpha times T minus 1/2 GT squared. Okay, now we know that, like the other problem, we know that at y max, that velocity in the y is 0. Okay, so if we go back up then to this equation, just like we did in the previous problem, then we can solve for t, can't we? We can get t, and this point's labeled point B up here on the.
Your document camera's out of focus.
Yeah, I just noticed that. It didn't like that. Something happened. Come on, you bugger. That's much better. Let me see if I put it up on. If I raise it up a little, maybe it'll behave. Even though, all right. Is that better? You guys can see that okay? Sorry, it can be fickle sometimes. Let me see if it make it a little flatter. This will all go away when we start again. All right. So here we have, so I'm going to go ahead and solve for t, and my t at B, so that means the time to get to point B vertically is going to equal 11.5 sine of alpha over gravity. Okay, so this equation is going to come back, because really what we're trying to figure out is, well, we have to figure out a few things first. First of all, we want to figure out the angle, and we also need to figure out the distance. But first, if we can find this angle here, that's going to help us a lot. So if we go back in to our y equation and we say that y to try to get to B, okay, equals 11.5 sine, and I know I wrote this again, but I'll write this before, but I'm going to write again, sine alpha times TB minus 1/2 GTB squared. Then I can put in some variable. I know that the height of y is 1.1, and that's going to equal 11.5 sine alpha. And now I'm going to substitute in this relationship here into TB. Okay, so what we're going to have is 11.5 sine alpha divided by TB, and then that's going to be minus 1/2 G, and then that's going to be times 11.5 sine alpha over G all squared. Okay, so now I have this big ugly equation, and so what I'm going to do is go ahead and simplify. And so if I simplify this, I end up with 11.5, and this is still 1.1, 11.5 squared over G times sine squared alpha. Sorry about that. And then that's going to be minus 1/2 G times 11.5 squared sine alpha squared over G, okay, squared. And so what we really get after we simplify this is we get kind of the same, this is 1, that's a half. So what I mean by that is this ends up being 11.5 squared over G sine squared alpha minus 1/2 11.5 squared sine squared alpha over G. Okay. And so if you think about, if we pull this out and that, that's really, this is like saying 1 minus a half, right? And so the final answer is just literally this, because if you take 1 minus a half, you get a half. And so we end up with 1.1 equals 1 over 2G, or 1/2 G, 1/2 over, I'm sorry, 1 over 2G times 11.5 squared times sine squared alpha. Make sense? So all I did was, this was like 1, this is like a half, subtracted 2, and that's what I have. So now I can solve. I know that essentially sine alpha is going to be equal to 2 times 9.8 times 1.1 all over 11.5 squared all to the 1/2. Okay. So what we end up with then is alpha equals 23.81 degrees. So a lot of steps, but you get the idea where we're going. So, all right. So again, you notice that it's this problem's really no different than the other one. It's just a little more algebra. And so hopefully your algebra is polished up, so you should be okay. Now we're not done yet. So we have the angle. That's great, but we still need to find the distance. So the good thing is that now that we found the angle, that makes the rest of the problem fairly easy. So if we go back to this drawing, if we know that the angle is 23.81 degrees, then we know that x equals x naught plus v naught in the x times time. And so given that v naught in the x is just going to be 11.5 cosine 23.81, that means that's equal to about 10.52 meters per second. Then what we can do then is we know that t here is going to be the same as the TB we found. And so we found that the TB, which we don't know yet, right? So we know we're going to use this equation and we need to find this. We know this is this, but we need to find that, right? So we go back to our relationship for TB, which was what? It was equal to, TB was equal to 11.5 sine alpha over G. So now we can substitute in and get our time. TB equals 11.5 sine 23.81 degrees all over 9.8. And we get a time of 0.473 seconds. Okay. So now that we know that, everything works good for the x equation, because now what we can do is just say x equals 11.5 cosine 23.81. And then that's going to be times the time of 0.473. So we know that in that case, then the distance x is 4.98 meters. So that's the maximum distance that this water. So the water coming out at 23.81 degrees can only go that far. or 4.98 meters. So the total length of the pipe really didn't matter, but the height did. We need to know that. Okay. So hopefully you're seeing a pattern here with these. And that's, what I'm trying to do is give you some kind of a semblance so that, for example, when we take the test, you say, oh, okay, this is a projectile motion, or this is a motion using derivatives or integration, or this is a relative motion problem, so that you can at least put these problems in buckets and then use the tools you have to solve them, as opposed to just being this big mishmash of different problems, all kinds of different stuff. All right. Any questions? Good. You guys are doing great. And I can't wait to be live again. It'll be much better than this, I promise you. So let's go ahead, look at one more. And so this one again is, as with all the dynamics problems, the understanding what is actually happening and applying it to the system is generally half the battle. And so here we have a wheel and we have water discharged onto the wheel, and we're given that the nozzle is 20 millimeters behind where the center of the circle is. That'll be significant. We know that the water comes out at a -6 degrees angle, and we know where points B and C are. So what we're trying to figure out is, what is the initial velocity of the water, or what's the range of the initial velocity, such that the water either hits B or hits C. So basically V to hit B, V to hit C. So we'll have essentially the lower realm and a higher realm. And so again, we have X motion with no acceleration, and we have Y motion only with gravity working. So let's go ahead and look at that. So if you have a circle template or something like that, it helps a lot to draw some of these, and definitely a straight edge. If you definitely have a straight edge, even a credit card, anything to make your drawings good, especially for the homework. All right, so let's look at this now. So here are our two wheels. And so what I've done is, here's one where we're trying to get to point B, and here's one where we're trying to get to point C. And so I'm sorry if that's not as good a focus. This says, this is essentially 30 degrees here. There we go, 30 degrees. And so this is just 10 degrees here, just like in the picture. All right. So like before, we have our fine range of V naught, so water falls between B and C. And other than that, we only know dimensions. So we know that this height from here up to where the water's ejected is 205 millimeters. We know it's behind by 20, and we know that the radius of the circle is 175 millimeters. Okay, so radius equals 175 millimeters. And so we know then, first off, if we just look at the water itself, we know that the water V in the X direction is going to be equal to V naught cosine 6 degrees, and V in the Y direction is going to be a negative V naught sine 6 degrees, since it's going down. Okay. And so we know then what we're probably going to have to use our free fall equation. So Y equals Y naught plus Vy naught times time minus 1/2 GT squared. All right. And so we know that the location of point B for its X and Y location, so I'm just going to write that here, point B, because we want to know where it is relative to the other point, is going to be, its X is going to be at 0.175 sine 10 degrees, and its Y is going to be, dimension is going to be 0.175, sorry. Erase that, make sure it's clear. cosine 10 degrees. All right, so we have those distances. And so the x location, or given our x location, x is our x naught equals, sorry, let me rewrite this. X equals x naught plus v naught x t. So if I rewrite that, what do I have? I have 0.175 sine cosine 10 degrees or should that be, yeah, that's sine. Sorry, I'm just looking at something that I wrote. Yeah, I apologize. It should be the x location, because what I'm trying to do is I'm trying to tell you what the x location is. So the x location of this is going to be 0.175, and what I wrote was sine 10 degrees. I'm not sure why I wrote cosine. So sine 10 degrees. And that's going to equal to the location, which is negative 0.02. So 20 millimeters is because it's starting at 20 behind, and then it's going this way over here. And then that's going to be plus the initial velocity cosine 6 degrees times time b. So if we solve for that, we get TB equals 0.0504 divided by V naught cosine 6 degrees. Okay.
Isn't the do you have your x's and y's for point B?
I'm sorry.
For point B, do you have your x's and y's swapped? Like the exponential and y dimension of point B?
I can't hear words you're saying. I'm sorry.
Have my mask on. Do you have the x and y for point B swapped?
So, well, x should be 0.175 sine of 10 degrees, right? So if this is 0.175, I want to know this distance here in the triangle, right? So wouldn't that be sine of 10 degrees times the radius for x?
Oh, right. We're looking at the angle from the vertical. Okay.
Yeah.
Okay.
Sure. No, thank you for pointing that out, because does that make sense then?
Yeah, that makes sense.
Okay, thank you. So we get TB, and so what we've done now is we've solved this equation for where the x position is by time. And so now what we can do is we could go ahead and write our y location equation. And so really this is another one of those power substitution problems. And so what we're going to do with our y location is we're going to do the same thing. We're going to have 0.175 cosine 10 degrees. And that's going to equal, again, in this case, oh yeah, 0.205. Sorry, I was looking at the O2. So in that case, the 205 is the initial height, which is this height here. That's where it's starting from. And then it's ending at 175 cosine 10. So it's starting higher than it's ending. And then that's going to be then plus V naught sine 6 degrees times TB. And so, and then minus, sorry, 1/2 G TB squared. So I got squished in there. So if I rewrite that, I have 0.175 cosine 10 degrees equals 0.205 meters minus V naught sine 6 degrees times 0.0504 divided by V naught times cosine 6 degrees. And so all I'm doing here is I'm substituting this TB into this and then rewriting it. So this is essentially that. And then minus 1/2 9.8 times 0.0504 divided by V naught cosine 6 degrees, all squared. Okay. So if we go ahead and simplify all this, we get negative 0.03266 equals negative tangent 6 degrees times 0.0504 minus 4.9 times 0.0504 all over V naught cosine 6 degrees, and that's all squared. Kind of ugly. So with that, we simplified even further, and we're actually able, and you can see that because V naught squared is the only variable, this doesn't have, this is a number, that's a number, we're able to solve for V naught. So if we simplify it further, and given time, I won't simplify it, but we end up with essentially V naught squared equals 0.45995, and you guys can check this on your own, or V naught equal to 0.678 meters per second. Okay. And so if you look again, and the reason I chose these three problems is because they all show how just using the basic equations that you learn in physics and some careful algebra, you can solve these problems that look initially a little intimidating. And so all we did again is we took the y location equation, we substituted in the fact that we know how far it's going in the x, because we know the physical location of B, and so we know how far we can tell the time based on that. We substitute it in, and then we solve. And so the second, the other one is essentially it's the exact same process for solving for the farther distance, because in the next one, all you're doing is solving for point C, and that just has a farther distance from B. So, but mainly if you should understand all this, that's the main thing. So any questions on this in any way, shape, or form? Okay, so I'm recording this, as I said. So the second lecture's up, I'll record this and put this one up too. So if you missed anything, you can go back and watch this award-winning video, the bowl of popcorn. You know, it's Friday night, so hey, make it a double feature. So, all right. So let me go, let's go and look at the long distance one and set that up. And so that one's going to point C. And so I'll set that up for you. And it's essentially, you set it up the same way. Again, we know that x equals x naught plus v in the x times t, or we know that 0.175 cosine 30 degrees And so here we're using cosine instead of sine because we're going with this distance because of where the 30 is, whereas here the 10 was here. So we have that, and then that's going to equal to its initial location, 0.02 meters, and then plus V naught in the X, which is cosine, actually not V naught in X, I'm sorry, it's just V naught. Just V naught, and then that's cosine 6 degrees. And then that's going to be times the time to get to C, or TC. So then again, we say TC is equal to 0.17155 over V naught cosine 6 degrees. So we have our TC, and then we go ahead. Yes.
Is that a negative 0.02?
Yes, it is. Thank you. And it was on my notes. I did see that. Thanks for pointing that out, though. And so, and then we have y. And so again, we're going to do the same thing with our y equation. We're going to say y is equal to 0.175 sine 30 degrees. Right, so that's our y. That's our y final. So our y initial is 0.205. So we'll rewrite that. So this is y initial, and then y final, of course, is actually, I'm sorry, y mixed up the lines. Actually, let's just make it easier. We know that this is where it ends up, so that's our y final, and that's going to equal 0.205, which is y initial, and then that's going to be minus V naught sine 6 degrees TC minus 1/2 G TC squared. Okay. So then we do the same thing. We substitute in this into that, and then we can solve. Okay. So I know you guys can do that, and it's actually good practice. So I would substitute that in, practice your algebra. It's up to you. But what you end up with then is you should end up with solving. Once you solve that in and solve for V naught, you should get a V naught equal to 1.207 meters per second. So essentially the range is 0.678 meters per second, less than or equal to V naught, less than or equal to 1.207 meters per second. So this is how you'd box your answer, because it gives the right number of sig figs and it's got the units. So I know I don't always put units up here. I don't know if that's a good or bad habit. It's a matter of style. If you want to carry units all the way through, that's one thing. The units are fairly simple here. I think when they get more complicated, it's probably better to carry them. But again, that's just a matter of preference. Okay. So that's it for this week. We survived the first week of dynamics. So far, so good, I hope. I will see you guys on Monday. I'll be in office hours, normal time, and then we'll have our lecture at 1. But go ahead. I hope you guys have a great weekend, and thanks for coming.
Thank you.
Thank
Thank
you.
you.
Thank you.
Thank you.